Right, so this is the final video of the energetics section. So this is part 3, and it's going to look at Hess's Law and the applications really of Hess's Law to various situations where you can work out enthalpy changes that you're asked of in a question. So first of all, think of a reaction, just a generic sort of A plus B goes to C plus D. So A reacts with B to give us C plus D. And for this reaction, we would find that we have an enthalpy change. There would be a change in energy for this. So there's an enthalpy change for this reaction. We'll call it the enthalpy change of reaction for the sake of argument. And that would have a value. Let's say that has a value of 413 kilojoules per mole. Now, that's a fairly straightforward reaction, but using this thing called Hess's Law, actually, we can work this out in a different way. And the reason is that Hess's Law essentially relies on this phenomenon, I guess, and that is that you must know the definition for this as well. The enthalpy change for a reaction is independent of the route taken. Independent of the route taken. You'll see various sort of definitions for this written in different ways, but it always has the same idea that the enthalpy change is the same no matter what route you take or what extra steps you take. And what that means is that ultimately the enthalpy change of this reaction will always be 413 kilojoules per mole. It can never be any different. Okay, maybe more theoretically than anything else. So what that means is that I could actually say, well, I'll go via an E and F step. And in doing that, I would find that, and we'll call this actually, I've changed this now to enthalpy change 1, and this can be enthalpy change 2. Enthalpy change 1 is going to be equal to enthalpy change 2, and I could keep going. I could say, well, I'll go to another step here, Z to another step here, Q to another step here, P to another step here, R, and then I'll finally end up at C and D, and still enthalpy change 3. It will be equal to them all. And so this is what Hess's Law really means. It means that no matter what you do to get from A plus B to C and D, provided you start with that and you end with that, you are going to have the exact same enthalpy change for that reaction. And this is this kind of, in fact, we can go past these intermediates, if you like. And that's important because it leads us into that we can work out enthalpy changes from information which allows us to go around the houses, so to speak. And we can produce something called thermochemical cycles, which sound a lot more difficult than they are. They are cycles, so they have this sort of appearance, this sort of blue one here, they look something like that, and they allow us to use calculations to work out an enthalpy change here. So we're going to look at an example then, and we can use the questions that you'll get on this will look at enthalpies of combustion and enthalpy of formation, and I'm going to start with enthalpy of formation, and you need to know a definition for that. So the enthalpy of formation, this is the enthalpy change, so the delta rate, the enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states and under standard conditions. What I mean by standard conditions is the whole 298 Kelvin and 100 kilopascals. A couple of examples then of what this actually means. So we could say, well, I want to know what how would I form carbon dioxide? So CO2. Well, carbon dioxide would be formed from carbon and from oxygen, and it's as simple as that. The enthalpy change for that reaction there is the enthalpy change or formation. And we can see it all balances up because we've got carbon plus oxygen gives us CO2, carbon dioxide. And we've produced 1 mole of this. Another example where we'd have to look at a bit different balancing could be something like if we're producing methane, of which case we would have H2 here, and we'd have carbon. Here, we would need to double this. And now we can see that we've produced 1 mole of compound from our elements. And if we were to be actually a little better on this, from our elements in their standard state. So we have produced 2 different compounds here. And again, that would be the enthalpy change or formation for that reaction. So really, whatever you've got, break it down into its elements, stick them together, and you'll end up with a compound. It's as easy as that. Now, if you can get your heads around this, then, and you can get your head around this idea that we can take a different route to get to an enthalpy change, then you can make this thermochemical cycle quite easily. Now I'm going to use an example of ethine, so C2H2 reacting with hydrogen to produce me, I'll just put this all in, give us some state symbols as well, to give me ethane. Now ethine is a hydrocarbon. It's one you don't really come across. It looks something like that. So a triple bonded carbon there. So this is ethine, hydrogen, ethane. Okay, so I'll go down the bottom here. What this relies on is that, and I'm going to go about this in a slightly longer-winded way than is necessary, but just to get the point across really. Once you feel comfortable with this, you can actually do this. You can get this done a lot quicker. But I'm really going to labour the point so that it hopefully makes some sense, because it's something where people can find this quite difficult. So what I'm going to say is that for this, I'm looking to calculate this enthalpy change here, the enthalpy change for this reaction. And I'm going to do so using given enthalpies of formation. Now you'd be given these in the question, and for this one here I've got the enthalpy change of formation of ethine is plus 228, and that's kilojoules per mole, but I'm going to run too far over if I do that. And then the enthalpy change of formation of C2H6 ethane is minus 85. I don't need to worry about the hydrogen, and the reason is, and that's the potential ask that as a question, why does the hydrogen not have an enthalpy of formation? Well, it's already in its standard elemental state. Okay, so we would be looking at hydrogen goes to hydrogen, which is fairly pointless. So we don't need to worry about the enthalpy of formation for hydrogen because it is in its standard elemental state. So we don't need to worry about the enthalpy of formation for hydrogen because it is in its standard elemental state. So let's go back to this then. Now I'm using enthalpies of formation, and what I do here is I like to think, well actually what does this mean? So the enthalpy formation of ethine, well that's the energy change required to make ethine from its constituent elements in their standard state. So ethine contains carbon and hydrogen, so to make ethine I would do carbon plus hydrogen goes to my C2H2, my ethine. And in doing that, I would balance up with a 2 there, and that's done. And so that's this number here. This 228 is the enthalpy change of formation for this reaction. On the other side, flip it over slightly. I've got C2H6, which is a similar idea. It's still a hydrocarbon, so I've got carbon plus hydrogen goes to C2H6. This time, change my numbers slightly. 2 carbons. I've got 6 here, I've got 2 here, so I've got that together, and there we go. This one has an enthalpy change formation of minus 85. Now, this is the bit people find more difficult, and you don't need to include this, but in my eyes, it makes it a lot more straightforward. I'm going to write it first and then come back to it, and hopefully it will make some sense in a second. So what I can say is at the bottom here, I'm going to put as my intermediate step here, like when I had E and F here. My E and F for this reaction is going to be 2 carbon, 3 hydrogen. I'll put that in a nice little box as well. Now you might look at this and you might say, well, I have absolutely no idea where that's come from. But then when I put in some arrows, hopefully it will start to make a slightly more sense. So what I've got then is I'm saying that this carbon and hydrogen react to go over there, and it will react to go over there. So actually what I'm doing is I've flipped this, I've taken this and I've flipped it over so that these are now in this bottom part and this is up there, and I've done the same this side. These are at the bottom part and this is up there. Now those astute people watching this will realise that this is 3 here, there's only 1 here, and I've written 3 there. Well, the reason is because we think about the entire reactants here. This is used to make this entire side. Well, I've got 2 here already, so my 3, 1 H2 goes over here, the other 2 would go here. But we don't need to worry about an actual enthalpy change for that because it's not becoming anything new, it's remaining as hydrogen. Whereas this side, my 2 carbons and my 3 hydrogens goes to make solely the ethane here, C2H6, which hopefully makes some sense. The next step on this, and actually really kind of one of the final steps, is we put these numbers back into these arrows. So over here, forming my ethine, I know it's a plus 228, and over here I know that's minus 85. So all these arrows representing, if you completely cover up this part, this arrow is representing the reaction between 2 carbons and 3 hydrogen molecules to produce ethane. And over here it's the reaction of 2 carbons plus 3 hydrogen molecules to produce ethine plus 2 H2 molecules. And the reaction there has plus 228 kilojoules per mole to complete that, and it has minus 85 kilojoules per mole to complete that. So in terms of now how this whole Hess's law ties in with the actual calculation of this enthalpy change here, is that I can say, well, I'm starting here and I want to finish here, but I can't go via there. So what I'm going to do is I'm going to go via this whole reaction here, and I'm going to end up over here. So I'm going to have to actually go against this arrow, but I'm going to go with this arrow because that's already pointing in that direction. So this arrow is pointing against the direction I want to go in, but this one's pointing with it. Now, when you go against an arrow in a thermochemical cycle, you reverse the sign. So actually here, I've now got minus 228, because it was plus before, it's now minus because I'm going against that arrow. Over here, I'm going with it, so it remains, and I like to always add these, even though I know you could just write minus 85, but I like the fact that it's plus minus 85, I think that makes it a little bit, makes a bit more sense. You add those together and you get 313 kilojoules per mole, minus 313 kilojoules per mole, I should say. And that's actually it done. That is the answer here. This is minus 313 kilojoules per mole. Hopefully that's made some sense. There's not really any other way I could explain that, I don't think. Key things of this are, this box actually isn't necessary. Provided you can get the arrows in the right place and you've got the right values on the arrows, you'll be fine. Key thing, I'm starting here, I'm going against this arrow, therefore I'm reversing that. I'm going with this arrow, keep it the same. Boom, add them together, there's your value. And I'm going to do one more now, but looking at it from a different point of view and not looking at the delta H of formation, the enthalpy change of formation. I'm going to look at the enthalpy change of combustion. So enthalpy change of combustion. Again, you need to know a definition. I do apologise, but blame AQA. The definition here is the enthalpy change when, very similar to one before, when 1 mole of a compound is burned completely in oxygen with all reactants and products in their standard states under standard conditions as per before, 298 Kelvin and 100 kilopascals of pressure. A couple of examples just so you can hopefully see actually what this means. I could say, well, what's the enthalpy of combustion for sulfur dioxide? Actually, that's a terrible example. It's going to produce sulfur dioxide. That's not what I mean at all. I mean, what's the enthalpy of combustion for sulfur? So it'll be sulfur plus oxygen to give me sulfur dioxide. Confusing my old age. I could say, what's the enthalpy of combustion for carbon? Carbon plus oxygen gives me carbon dioxide. You could do anything really. You could go one further and you could say, what's the enthalpy of combustion for methane? It would be CH4 plus O2 gives you CH. No, it wouldn't. So I am getting old. CO2 and H2O, and then you would balance it up accordingly. So 2 here, balance the ones there. 4, 4, 2 here, 2, 2. Yeah. The key thing here is that I'm keeping this. This is my thing that's being burned every time. This is my compound. This needs to remain as 1 mole. Okay, this needs to remain as 1 mole. And I often teach my students that when you're doing these combustion reactions, use halves here rather than double it up. If you end up with 3.5 here, fine, doesn't matter. Keep this as a whole, even at GCSE, because it's just good practice really when you look at these enthalpies of combustion, for example. So, going to look at this as an example and actually tie together some numbers here and see if we can't work out what's actually happening. So I'm going to use exact same case as before, mainly so you can see that Hess's law actually is what it says, and it actually does work, well, based on the values that I'm giving you anyway. So same as before, ethine reacting with hydrogen to give me ethane. Now this time, I'm still looking for the enthalpy change of the reaction, but I'm going to use this time some delta H, the enthalpy changes of combustion instead of formation. So the enthalpy change of combustion for ethine is equal to minus 1301. Enthalpy change of combustion for H2 is equal to minus 285. And enthalpy change of combustion for ethane is equal to minus 1560 kilojoules per mole. So obviously using those values of kilojoules per mole the entire time. Okay, as before, I'm going to write out what these actually mean, and again I think it just helps you to get your head sort of your head straight, and so you can actually work out what's happening. Otherwise it just becomes very, very messy. Right, first one, enthalpy of combustion of ethine. So we've got ethine, we're combusting it, that means obviously we're adding oxygen to it, completely burning it, and we're going to form CO2 and H2O, and I know that because it's a hydrocarbon. When it reacts, we'll oxidize the carbon and the hydrogen to form the carbon dioxide and water, as with any sort of reaction that contains carbon and hydrogen. I'll balance up in a second. My other one on this side is going to be my hydrogen combusting to give me H2O. That's why hydrogen's a great fuel, no carbon dioxide, no global warming, blah blah blah. And I'll balance this up, 2.5 here, 2 here. Over here, I'm going to put a half in. Reason for this here, obviously, is that I can't change and start doubling up this. Normally, if this was a reaction, actually, I'd probably put 2 and a 2. I'm not going to, because this one I need to stick to the enthalpy of combustion. Yeah, we've got 1 mole of a compound is completely burned, so that needs to remain as a 1 mole. Other side, ethane plus oxygen. Should have given myself a little bit more room here, but that's fine. Carbon dioxide plus water, 3 there, 2 there, 3.5 there. Apologies, that's not the best thing I've ever seen. It's a bit sloppy, but there we go. Okay, so I'm going to have a little intermediate box again. And this intermediate box this time is going to be as follows. It is going to contain, choose a nice colour for this. Yeah, there we go. it is going to contain 2 CO2 and 3 H2O. Easy way to work this out. The side that only has one thing on it, it's going to be equal to that if you like, but you can get it from either side. So we know that when we combust this, it will form 2 CO2 and 3 H2O, exactly as we've got written here. When we combust this, it will form 2 CO2 and 1 H2O, which means we're missing 2 H2Os. That whereabouts of that is from this one here, because we have 2 moles actually being combusted, so we have twice this. So 2 CO2s, 1 H2O from here, 2 more H2Os from there takes us to the 3. So as before, we're sticking the arrows. So if we go across, put in some arrows here. This time I'm combusting these, therefore it's the enthalpy change to combust this to make it become this. So my arrow is actually going to go down. I'll put the box around here again. This is going to go down, and this one is also going to go down. And again, all I'm doing is I'm really flipping these around. So this is the intermediate stage here, the products, and I'm just reacting. So this here, reaction of that to produce this, that to produce this, that to produce this via combustion in all 3 cases. And it's no different to before, actually. We just follow the exact same route. We go start and finish, and we just work it around. We go around here, around here, around here, around here, around here, around here, and then we end there. And exactly as before, if I go with an arrow, brilliant. If I go against the arrow, reverse the sign. Now these are both on my reactant side, so I'm going to go with both these arrows. And if we look at here, we've got minus 1301 here. We've got minus 286 here, but remember we have 2 of them. And then we have minus 1560 here. So just quickly, these values are the true values. I'm not going to write these in as reversed ones. I'm writing them in as the true values, and then when I come to calculate, I will reverse if necessary. So I'm going to go with this minus 1301, and I'm going to add to that 2 times minus 286, and then I'm going to add to that, going this way, positive 1560, and that will give me a value, and that value, when you add it up, you should find comes to minus 313 kilojoules per mole, which, if you remember from before, go across, there was my enthalpy change of formation. There's my value, minus 313, there it was there, I calculated it, go across, minus 313. And this is proof, really, this whole Hess's Law thing actually kind of does work. I haven't gone via the same intermediates, I've looked at different values, but ultimately I've actually found the same enthalpy change for this reaction of ethine plus hydrogen to give me ethane. So it doesn't matter which ways I go, I end up at the same point. Okay, I'm going to leave that there. If you have any questions about this at all, please do comment, and if need be, I'll add some more stuff in if people need that. But I hope that has been of some help for people if they were struggling with this concept of Hess's Law and thermochemical cycles.